third talk of the session will be given by Jennifer Paykin on Qudit quantum programming with Projective Cliffords.
Great. Okay, microphone's on. Okay, yeah, thank you. So I am going to talk about sort of a different perspective on quantum programming. Normally, in the usual model, we're thinking about unitaries as transformations on states, right? So it takes a state to another state. But I claim that in some cases, it's actually going to be more useful to describe a unitary by its conjugation action on the multi-qubit Pauli group. So this Pauli group is the unitaries that are generated by X, Y, and Z. And in fact, any one of them can be written as a combination from the other two. So really, we only need to consider two of these, like X and Z, in some senses. Okay, so this is especially true for Clifford operators, which are exactly the unitaries that preserve the Pauli group under conjugation. So the Clifford operators are the ones that when you look at their conjugation action, the result, UP, U dagger, is also a Pauli operator. Okay. Furthermore, any two Cliffords with the same projective action, actually any two unitaries, I should also say, yes, this is the same Clifford group as those generated by the Clifford gates, like Hadamard, phase gate, and C0. So I will note that any two Cliffords with the same projective action, in fact, this is really true of any two unitaries with the same projective action, are indistinguishable up to global phase. So we can really consider the equivalence class of those unitaries up to conjugation. And in this case, we're going to call that the projective Clifford operators. So rather than thinking about unitaries as a map from states to states, in this talk, we're going to be thinking about projective Cliffords as a map from Paulis to Paulis. Okay. So as a programming language theorist, when I started thinking about Pauli's Cliffords this way, I said, oh, okay, well, let's build a language where we can write functions we can write functions over the Pauli group, and well-typed functions should correspond to projective Cliffords. Turns out that there's some details we need to work out in order to make that happen, but it does in fact work. So we call this language in the paper LambdaPC for projective Clifford. Okay. I would like some properties to hold of this language. I'd like this to be a pure lambda calculus with a well-defined operational semantics. I would like these functions, these well-typed functions, to still be able to be compiled to circuits. I'd like to be able to run them. And I would ideally like this language to enable new ways of thinking about quantum algorithms. So by sort of changing our perspective and how we program these systems, we will hopefully be able to build new kinds of algorithms, or at least think about algorithms in a different way. Okay. So this middle part, the compilation to circuits, sounds quite hard, but it isn't. Or at least it's understood very well, so it's all worked out. So So this is using the same ideas as Pauli tableaux, if you've seen those. Basically, the idea is the following. So every Pauli can be written in the following form. I'm going to write a power of I followed by a bunch of x's and z's. So for, if this is an n qubit Pauli, it's going to have like possibly an x at qubit 1, possibly a z at qubit 1, and so on for every qubit. And so the power of the xi, zi is, those are going to be just bits, right? And this works because y is, I'm writing this with this star operator, it's x star z. And so, any single qubit Pauli is either identity x, z, or y. Okay, great. So this is like a little bit valued encoding of the Paulis. I will also note that projective Cliffords distribute over this star operator. And so as a result, we can express projective Cliffords in the following way. So all we need to do is say, what does the projective Clifford do to x1? What does it do to z1? What does it do to x2? What does it do to z2, et cetera? Okay? And so we can kind of list this out in this chart. This chart has 2n entries. And often you'll see Pauli tableaux written out actually as like bit encodings. Okay. So this is an efficient representation of projective Cliffords, right? It's like the size is on the order of n squared. And in fact, it also enables efficient simulation of Clifford circuits. Side note, Cliffords are not universal for quantum computing. Important to note, but they're still extremely relevant for all sorts of different applications. So like including but not limited to quantum error correction. That's a really big source where thinking about Cliffords and thinking about them in this framework as maps on the Pauli group is in fact a very natural way of working with or building error correcting codes. So as a result, there has been a lot of research and interest into this efficient simulation of stabilizer circuits, as well as efficient synthesis into Clifford circuits. And in fact, these synthesis techniques are like among the best synthesis techniques for circuits. So you see them a lot in optimization techniques. Okay. I will note, however, that these tableaux are data structures. Like they're not really programmable. They're not really compositional. And so we need to do a little bit of work in order to figure out how to really program them. Okay. But before we talk about that, I want to go through a few examples. So let's think about the Hadamard operation as a projective Clifford. So this is the usual Hadamard unitary, right? And we can tell that it's Clifford because if you compute out what it does to x and to z, we can see that we still get Paulis at the end. It sends x to z and z to x. Okay, well, here's how we would write that in LambdaPC. So here we have a function from Pauli to Pauli. So when I write Pauli in this type, I'm referring to a single qubit Pauli. And then if I have multiple qubits, I'll have Pauli tensor Pauli or something like that. Okay. I'm distinguishing the type of projective Cliffords using these bars in the type. So it's like a bar and then a type, lolly, other type. I'm also using these bars to distinguish the sort of pattern matching syntax within the projective Clifford. So I want to say, so I'm saying like, okay, so if the input is an x, then send it to z. If the input is a z, send it to x. And this is sort of like a Haskell style pattern matching syntax. In the paper, we have a core calculus, which uses a case statement. So this is just syntactic sugar. Okay. So now that we've written this function, we should be able to apply it to any Pauli in the single qubit Pauli group. So let's see what happens when we apply it to y. It's going to evaluate as follows. So first of all, it will notice that y can be written as x star z. Then it'll distribute the function over the star. And then it will use the definitions to produce z star x, which it knows is negative y. Okay, let's look at another example. So here we have a 2-qubit gate, the controlled NOT operation. And once again, we can sort of fill out this little table to see what does C naught do to x1, z1, x2, z2. And we can use that to define our projective Clifford. Now, there's not necessarily, so far we can basically just like translate these tableaux into pattern matching form, which is maybe not that interesting. But once you have this language, this structure, you can do a lot more things. So here's just one example. We have more examples in the paper, but here's an example of the fact that any Pauli is also a Clifford. Okay, so I would like to write a function that that takes as input a Pauli and then lifts it to a projective Clifford. And it's a Clifford because of the following fact. This is a fact of the Pauli group. Any two Paulis either commute or anti-commute. So in other words, PQ is plus or minus 1 QP. And that sign, the plus or minus 1, can be easily calculated. It's written omega. And we can actually write it down in the non-projective Clifford fragment of LambdaPC. So omega itself is not a projective Clifford, right? It takes in two Paulis and it returns a sign. But it is a linear transformation. So we can define it by how it acts on the basis elements. So omega will take in xi, xj. So if omega sees xi, xj, well, xi and xj are always going to commute with each other because x commutes with x. So the result should be 0. The same is true for z. Z always commutes with z. For xi, zj, if I is equal to j, then they anti-commute. Otherwise, they commute. And similarly for zi, xj. Okay. So that's the definition of omega. We can now write this Pauli to Clifford function that takes as input a Pauli, P. This is of type any type tau, any Pauli type tau. And then it's a projective Clifford, so it takes in another Pauli, Q. And it returns Q. I'm sorry, this is a typo. This right here should be oh, it is a Q. Okay, yes. So it returns Q with a sign. And that sign is omega of P applied to Q. So this syntax with the angle brackets, that's indicating the sign in our syntax. Okay. So we're able to write down these functions, but I'd say there's still work to do because I haven't said anything about the type system. So how do we actually check that one of these functions does correspond to a valid projective Clifford? So what do I want from this type system? So my first question is, when does this function from Paulis to Paulis actually correspond to a projective Clifford? So as a function, it needs to be a center-fixing automorphism on the Pauli group. That doesn't really tell me how to define a type system for that. The type system that I want should be characterized by properties that can be checked efficiently by a type system. And it should be appropriately compositional in some way. Okay. So to figure out how to characterize these functions, I'm going to look at the encodings that we were talking about when we were talking about the Pauli tableau. So we can think about that encoding as like breaking the projective Clifford down into two parts. So it's going to take as input a Pauli delta V, and it's going to return plus or minus delta phi of V, where that function phi is a function of the input Pauli, so the input vector. And in addition, that plus or minus is also going to be a function of that input vector. Okay, so finding the properties for what this function, the function from Paulis to Paulis takes, can be expressed in terms of the properties of mu and phi. Okay, well, what are the properties of mu and phi? Well, it turns out that can be a little bit complex. It sounds unintuitive, but to make it easier to explain those properties, I want to take a jump from qubits to Qudits. If you remember, the title of the talk is Qudit quantum programming with projective Cliffords. And in fact, the entire system that we have in the paper is generic over Qudits. And the reason for that, there can be several motivations, but one of the reasons for that is that it actually guides us how to find these, the properties of these encodings. So, so qubits, right, are a superposition of 0 and 1. Qudits are a superposition of 0 through d minus 1, just like classical dits are 0 through d minus 1. Okay. So the reason why this is relevant is because it turns out that encodings of projective Cliffords for odd dimensions is relatively straightforward. So we can write every projective Clifford in the following form that sends delta V to zeta of mu of V, delta phi V. So here zeta is a primitive dth root of unity, right? So just like previously we had -1, now we have zeta. And so just to be clear, this V is going to be pulled, this is like the vector V, the font is different, but the vector V is going to be pulled from the uppercase set V, which is 2n dits, basically. And the function mu goes from V to a dit, and the function phi goes from V to V. Okay, so what properties do mu and phi have? Well, mu is going to be a linear transformation, phi is going to be a linear transformation, and in addition, phi must be a symplectomorphism. And what that means is that phi respects this symplectic form, which is this function omega that we saw before. So in other words, phi has to respect, like the projective Clifford has to respect the commutivity relations of the Paulis that it maps. That's the connection there. Okay, so I will claim, and we'll come back to this in a little bit, in just a couple minutes, I claim that these properties can be enforced by a type system and are appropriately compositional. We'll come back to that. Problem though, we may care quite a bit about, not just about qudits of odd dimensions, but for example, qubits, which do not have odd dimension because that has d equals 2. So what happens when we look at these encodings for even dimensions? Unfortunately, it doesn't work out quite as well. You can still build something. You can build a variety of different encodings. But sort of the one that you might come to fairly naturally looks something like this. So it has the same structure as before. But now it's structured a little bit differently. So the vectors V come from some other set V prime, which are dits, but where the dimension is 2D, okay? And then mu takes that V prime to regular dits, and then phi takes V prime to V prime. Furthermore, this mu may or may not be linear. We don't necessarily know what constraints it's going to have. Phi can be linear. We can choose this encoding so that phi is linear. But then it's only a symplectomorphism if mu is linear, but we don't necessarily know what properties mu is going to have. So this is sort of not a way, this is sort of not a way to understand what properties we're going to get here. Okay. So my co-author Sam and I, in some previous work, worked out a different encoding of projective Cliffords, which has some quite nice properties that work out well for this application. Okay. So fact one is that in the condensed encodings, Qudits are going to be treated uniformly whether D is even or odd. So we don't have, when we're working with these encodings, we don't have to worry about the dimension D. Okay. In this case, we can describe these projective Cliffords as, again, functions from delta B to delta phi of E with this mu coefficient. The only caveat is that this sort of works for delta B being like a basis vector. So delta B has to only be xi and zi. We'll come back to that in a second. OK, so with that constraint, we get these nice properties again. We have mu goes from V to dits, right? Z mod dz, and phi goes from V to V. So, and again, V is only talking about D. It's not talking about 2D in some cases. OK, so we have these properties that mu is a linear transformation, phi is a linear transformation, and phi is a symplectomorphism. Great. And the caveat is that, OK, so this is how this function acts on B. And the caveat is that to evaluate this, the projective Clifford on an arbitrary Pauli, delta V, we need some kind of phase correction. So we need a plus or minus 1. And figuring out that phase correction is maybe it's not linear. It's like maybe not so easy. But we have formulas to work out how to do it. OK, so this condensed encoding, this is going to be our structure for our type system. So our type system for projective Cliffords has the following form. And it uses linear types to enforce that property of linearity for both vectors and the phase function phi. It uses a special symplectomorphism check to check that symplectomorphism property. Doing that check in practice could involve a special solver that's a special solver using SMT solvers, or hopefully in the future we'll come up with a better algorithm for doing that check, but it does work. And then those phase adjustment computations are all wrapped up in beta reduction. So as the user, you don't have to worry about what that sign is, what that sign reduces for, because that's all going to happen in evaluation. Okay. So to wrap up, in the paper, we've got a bunch more examples about programming, especially with Qudits rather than just qubits. We have worked out a case study that describes how you can write error-correcting codes in this framework in quite a straightforward way by describing how they transform the Pauli group. We also give a categorical semantics for those condensed encodings in a way that corresponds to our type system via Curry-Howard. And of course, we give all the details of the type system and operational semantics. Finally, we also build up some additional data structures and talk a little bit more about compiling to circuits. We have some work in progress implementation, which is available on GitHub. And we're also really excited about extensions of the language to things like stabilizer semantics that involves measurement, but also to in general, universal quantum computing in some interesting ways. So I think that's all we have, and I have a couple minutes for questions, I hope.
Yeah, indeed, we have a little bit of time for questions.
Thank you, great talk. I wonder if you attempted a completeness proof, because your Pauli tableau formulation looks like a bit like of a saturation, and so I wonder, did you try to prove, like, say, that all the correct programs are well typed?
We do have a completeness proof. Yes, every projective Clifford, or every projective Clifford can be expressed in this language. And that is based on the completeness of the condensed encodings as well. So,
thanks.
Hi, thanks for the talk. You mentioned the, I can't remember the word you gave it, but the thing that checked the symplectic form was checked by an S&T solver. Do you know if this is sort of a decidable fragment of S&T solving? Or more in general, do you know that your type system has decidable type checking?
This should be decidable. It's all in terms of bit vectors.
So it should be, it should fall in some decidable fragment of the S&T system. Okay, thank you.
Yep.
Other questions? I was just curious about linearity, because you mentioned linearity at some point. Do you enforce a strong form of linearity, so every function is linear, or do you have things like comonads, which allows you to copy maybe parts of programs that maybe do not refer to qubits?
Yeah, so we have, we do add in the nonlinear variables. So it's not shown in this, but we have like an additional context for nonlinear variables, and only the things of Pauli type are treated linearly.
Okay.
Yeah.
Okay, let's take the speaker then.
Yeah.